We're going to be looking at our logarithmic functions, which are the inverse of our exponential functions. And a logarithmic function will be written in the form of y is equal to log base b of x. And that's equivalent to b to the y equals x. Now, this is where we write it in exponential form. This is where we write it in logarithmic form. Now, one of the things that has to be true for our logarithmic equations is x has to be greater than 0, b has to be greater than 0, and b cannot be 1. Cannot equal 1. Now, if you remember back when we were talking about our exponential functions, our base couldn't be 1. So that's going to be true also here, and our base had to be a positive number. So that's still going to be true. And if you take a positive number and you raise it to a power, then you're going to get a positive number. And so that's why x ends up being positive. Now, the way that we read this is y is equal to log base b of x. And we're going to be looking at changing from logarithmic form to exponential form. So if you learn to read this correctly, then you know where several of the things go. This is log base b of x. Notice over here, b is your base. Now a logarithm always equals the exponent. So y is your exponent. And then you have your number, the log base b of a number. So y equals log base b of a number is equal to b raised to the y is equal to that number. So if we had 3 is equal to log base 7 of x, and we want to write that in exponential form, well, our base is 7. A logarithm equals the exponent, so our exponent is 3, so 7 cubed equals x. 2 is equal to log base b of 25. Well, this would be b raised to the second power, or squared, is equal to 25. This is your base. Logarithm always equals the exponent. Log base 4 of 26 equals y. So 4 to the y is equal to 26. Now, you should be able then to take something in logarithmic form and write it in exponential form. And you need to be able to take something written in exponential form and write it in logarithmic form. So if we have 2 to the 5th equals x, we want to write this in logarithmic form. Well, 2 is our base, so log base 2 of x of our number equals our exponent, equals 5. A logarithm always equals the exponent. If you'll remember that, it'll help you in a lot of these problems. B cubed equals 27. Well, that would be log base b of 27 equals 3. E to the y equals 33. So that would be log base e of 33 equals y. Now, when our base is e, when it's the log base e, we have another way of writing that, and that's called a natural log. So you'll also see this written then, ln 33 equals y, the natural log. And when you see this, then you know that's the same as the log base e, that your base is the number e. And we'll talk about that just a little bit more. We want to look at evaluating our logarithms. And so if we had log base 10 of 100, well, we want to know what this equals. So let's just go ahead and say equals y. There's several ways of evaluating it. One is we could write this back in exponential form. 10 to the y equals 100. Well, when we were looking at our exponential form, we found if we could get our bases to be the same, and 100 is 10 squared, then our exponents have to equal. So log base 10 of 100 is 2. If we have log base 3 of 3, and we want to know, well, what does that equal? We want to evaluate it. So writing it in exponential form, 3 to the y equals 3. Well, our bases are the same, so that means that our exponent had to be 1. Or log base 3 of 3 equals 1. If we had log base 36 of 6, and we wanted to know, well, what does that equal? So it equals what? Well, 36 raised to the y equals 6. And again, we could write 36 as the square root of 36. So 6, well, 36 is 6 squared raised to the y equals 6. So 6 to the 2y equals 6 to the first. So 2y equals 1, and y equals 1/2, which was what I was saying up here. It's going to be the square root of 36 equals 6. So that meant that our exponent had to be 1/2. Log base 36 of 6 equals 1/2. Let's say that we have log base 3 of 1 over the square root of 3. And we want to know, well, what does that equal? Well, this means 3 to the x equals 1 over the square root of 3. Okay, we'd like to get these bases to be the same. We know that this is the same as 1 over 3 to the 1/2. And we know that if we wanted the reciprocal of this, then we could write it with a negative exponent. 3 to the negative 1/2. Remember, a to the negative x was equal to 1 over a to the positive x. So 3 to the negative 1/2 is the same as 1 over 3 to the 1/2. So in this case, x is negative 1/2. And therefore, we can go about then and evaluate our logarithms. If we look at one more here, and this one's going to look a little strange, but we have 7 raised to the log base 7 of 23, and we want to know what that equals. We're wanting to evaluate it. So equals x. Okay, again, if we'll write this back in exponential form, then, well, or let's write it, instead of writing it in exponential form, let's write it, take the log of both sides. We could go through and we could do that. And so if we did, then it would be log base 7 of x is equal to log base 7 of 23. It was written in exponential form. We wanted to write it back in logarithmic form. So log base 7 of x is equal to whatever our exponent was. And so we can see here then that x had to be 23. So you should be able then to evaluate logarithms or exponential functions. Now, we have some basic properties for our logarithms that make working our problems a lot easier. And a lot of the problems that I just went through, we did this. So in looking at our properties, the first one that we're going to look at is that log base b of b equals 1. When the base of your log is the same as your base, then it's going to equal 1. And we did a problem like that right here, and where we have log base 3 of 3 equals y. Well, if you notice, it equaled 1. The base of the log was the same as the base of the number. And so when you have that, and you have a problem along that line, let's just say that we had log base 6 of 6, well, it's going to be 1. We don't have to go back and write it in exponential form because we know the answer. Right, a second property that we're going to have is log base b of 1 equals 0. Now, we didn't do one of these a while ago, but if we took this and we wrote it back in exponential form, let's just say we have log base 5 of 1, and we want to know what that equals. Well, we're asking 5 raised to what power equals 1. And we have a property that says any number raised to the 0 power is 1. So our x had to be 0, had to be 5 to the 0 power. So no matter what your base is, if your exponent ends up being 1, then that meant it had to be raised to the 0 power. And so that helps us a lot as we go through in evaluating our problems. So those are some basic properties. Now, we also have what are called the inverse properties. Which says log base b of b to the x equals x. Now that goes along with this problem because when no exponent is shown, it's understood to be a 1. So our exponent there was 1. If we went through and we looked at an example, log base 7 of 7 to the 8th equals what? Well, writing this back in exponential form, 7 to the x is equal to 7 to the 8th. So x had to be 8, whatever that exponent was. So if we had log base 5 of 5 squared, then that's going to equal 2. When the base of the log is the same as the base of your number, then it's going to equal the exponent. And we could have really just done this problem. That actually would be a 3. We could have done this one and not had to do this one up here. Because up here, if we went through with that, our exponent's understood to be a 1. So this property actually takes care of that one also. But we usually go ahead and put that one separately just because it makes it a little bit easier. And then the other inverse property, you won't see this one quite as often, but it goes along with the problem that we had. B raised to the log base b of x. Okay, the base of my number is the same as the base of my log. And so that's going to equal x. And if we look back at a problem that we did earlier, right here, the base of my number is the same as the base of my logs, and it equaled then the number there. And we went through and actually worked that part out, and we could do the same thing on this one. So these are some of our basic properties with our logarithms. And that will help us then as we go through and we start solving them. We'll look at some problems a little bit later where you can go through and just solve the problems and evaluate them. A lot of times evaluating them without using a calculator. Okay, we want to, for just a little bit, go ahead and look at our graphs of our logarithmic functions to see what ends up happening with them, and looking at our properties for our logarithmic functions. Let's take a graph that we did with our exponential functions. If we wanted to graph f of x equaled 3 to the x. Well, we've graphed this before when we dealt with our exponential functions. If you remember, our domain was negative infinity to positive infinity. We crossed the y-axis at 1. And we actually, if we just picked our points, 3 to the negative 2, if you want to make a table, you can. We've done that before. 3 to the negative 2 was 1 over 3 squared, or 1/9. 3 to the negative 1 was 1 over 3. 3 to the 0 is 1. 3 to the first is 3. And 3 squared is 9. So we could actually go through and just graph those points. We had our points. At 1 we're at 3, and 2 we're at 9. And then we could do our graph. Okay, what we want to do is we want to graph this in the form of a logarithm. And so we might want to graph g of x is equal to log base 3 of x. Well, if we wrote that back in exponential form, that would be 3 to the y equals x. So if you notice, what we're actually doing is we're doing the inverse here. If I went back and just wrote this, let me do this for a second. Y equals 3 to the x. If you remember when we wanted the inverse functions, we would switch the x and y. And so we would switch our x and y, and then we would solve for y. Well, that's the inverse then of an exponential function. So if you notice, that's what I have right here. I've got the inverse of this exponential function. I have y is equal to log base 3 of x. And so I've done my inverse function. Okay, and we could go back and actually, if I wrote this with the y, if I wrote it back in logarithmic form, it would be log base 3 of x equals y. So this is going to be my inverse of this function. It means my x's and y's are going to be switched. Now, to graph this, it's a little bit different when we graph this. And if we make a table, because we're used to picking our y's, substituting in and we're picking our x's, substituting in and finding our y's. What we're going to do is we're going to pick our y's because those are the problems that we can actually do. Well, if I do that, 3 to the negative 2 is 1/9. 3 to the negative 1 is 1/3. 3 to the 0 is 1. 3 to the first is 3. 3 squared is 9. And you can see that my x's and y's just switched. And that's what happens when we do an inverse. Now when I graph it then, what I have is 1/9 is negative 2. 1/3 is negative 1. 1 is 0. 3 is 1. And 9, 2, 4, 6, 9 is 2. And so if I graph this, then my graph of the inverse will look something like this. And that's my logarithmic graph. These two will be symmetrical. Tests that we had to see if some things were symmetrical was to see if they were symmetrical about the y equals x, about our identity function. And so those would be symmetrical. We've just switched our x's and y's. Let's look at another one that we can graph. Okay, we want to graph these two functions. F of x is equal to 1/4 raised to the x power. And g of x is equal to log base 1/4 of x. Now you can see that these would be inverses of each other. This would be y is equal to 1/4 to the x. Okay, log base 1/4 of x would equal, or of y, would equal x. Uh, of x would equal y. I'm sorry. I'm stumbling over some of my things here lately. So let's go through and let's graph this one. We're going to pick our values for x, and so we're going to pick -2, -1, 0, 1, and 2. Now, if I raise 1/4 to the -2, remember the negative says do the reciprocal, so that's going to be the same as 4 squared or 16. 1/4 to the -1, that would be the reciprocal, which is 4. 1/4 to the 0 power is 1. Then we have 1/4, and then we would have 1 over 16. So if I graphed those, at -2, I'm way up here at 16. At -1, I'm at 4. 0, I'm at 1. 1, I'm at 1/4, and then 1/16. Sorry. So my graph would be coming down. And again, my x-axis would be an asymptote. Now, if I wanted to graph this one, what I need to do is write it back in exponential form. So 1/4 to the y, or g of x, is equal to x. A logarithm always equals the exponent. Okay, when I make my chart here, then I'm going to pick my y values, -2, -1, 0, 1, and 2. And I'm going to find my y values. So 1/4 to the -2 would be 16. And those are the reciprocals. 1/4 to the -1, I'd want the reciprocal. That would be 4. 1/4 to the 0 is 1. 1/4 to the first is 1/4. And then we have 1/16. And so again, you can see that my values, my x and y values just switched. So if I graph this, way out here at 16, I'm at -2. At 4, I'm at -1. At 1, I'm at 0. 1/4, I'm at 1. And 1/16, I'm at 2. So what my graph is doing here is we're coming down. We cross. And then we would go out to our value. And again, these are inverses of each other. They're going to be symmetrical about y equals x. And so these are our inverses. Now, one of the things that you might notice then is there were some characteristics for our logarithmic function. We've already talked about the characteristic of our exponential. In our exponential, our domain was -infinity to +infinity. Our range was 0 to +infinity. In our exponential, we always cross the y-axis at 1. And we talked that if our base was between 0 and 1, then we were decreasing. And if our base was greater than 1, then we were increasing. And so we had some specific characteristics. Well, for our logarithmic graph, we have some specific characteristics also. One of the first things is our domain and range. In our logarithmic, our domain is from 0 to +infinity. Notice our y-axis was our asymptote. There was no way that we were ever going to get 0 for x because we had a value raised to an exponent. And so we would never get x equals 0. So our y-axis then ends up being our vertical asymptote. We crossed the x-axis at 1, 0, which was the inverse of where we crossed the y-axis in our exponential. And when our base was between 0 and 1, we were decreasing. Back on this other one that we did, our base was greater than 1, and so we were increasing. But we still had a vertical asymptote at x equals 0. Our y-axis was a vertical asymptote. We still crossed our x-axis at 1, 0. Our domain was still 0 to positive infinity. Our range was negative infinity to positive infinity. So all of those characteristics that we had, our domain and range just switched. When we had our exponential, negative infinity to positive infinity was our domain, 0 to infinity was our range. So we've just switched. On our logarithmic graph, the domain is 0 to positive infinity. On a logarithmic graph, our x-intercept is 1. On a logarithmic graph, the y-axis is a vertical asymptote. If our base is greater than, that should be greater than 1. Greater than 1. The function is increasing. If the base is between 0 and 1, the function is decreasing, and the graph will always be smooth and continuous. And you can deal with some of the transformations, just like we've dealt with before, of the undoing what's with the x, we undo, and our y value. Let's just look at a couple where we do it by transformation. If we wanted to graph, let's say we wanted to graph that y is equal to log base 2 of x plus 2. Now, what we have to know is our parent function of just what y is equal to log base 2 of x is. So we need to look at our parent function, which would be 2 to the y equals x. If we made our table and got those points, now it's our logarithmic function, so we know we're going to be crossing at 0, 1. Our base is greater than 1, so we know we're going to be increasing. So those are some things that can help you as we go through. But let's get some specific points. So 2 to the negative 2 would be 1/4. 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the first is 2, and 2 squared is 4. So we have our 1, 0, 2, 1, 4, 2, and then our small values. So that would be our parent function. And it would actually go up just a little bit slower than that. Now, all that happens here is we're changing our y values. And so all of our y values, we would undo that, so they're all going to go 2 units to the left. And so let me go back and just draw that, just see if I can draw that just a little bit better. Don't know that it's going to let me just erase it, because it's kind of hard to see my points there. These are not the easiest things to draw on this. So we've got 2, 1, 4, 2. And if we went out to 3, then we would have 2 cubed would be 9, 8. So we would have 8, 2, 4, 6, 8 would be 3. And then we have our values that are very close. So let's see if I can draw that just a little bit better. Okay, then what we would be doing is just moving our points 2 units. So we go 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. And what would happen was x equals -2 becomes our vertical asymptote. All of our points just shifted over 2 units. If we wanted to graph y is equal to -2 log base 2 of x. Well, we would take our basic log base 2 of x, which we just went through and did. We had at 1/4 we were -2. At 1/2 we were -1, 0, 2, 1, 4, 2, and 8, 3. So that was our basic graph, what we would call our parent function. And all this does is multiply those points by -2. And so it's going to reflect it as we go through. So at here we had -2, so times -2 would be a +4. Okay, here we were at -1/2. At -1/2 we were at -1, so times -2 would put us at +2. 0, we're still going to be at 0. At 1, here we're at 1 times -2 would put us at -2. We're at 2 times -2 would put us at -4. And 3 times -2 would put us at -6. So again, what that did was it reflected us across the x-axis, the same as it's done with all of our other graphs. And so all of the changes that we made with our other graphs, we would do the same. Back here, if when we looked at this one, that changed our x value and we undid it. If we had had a plus 3, then that would have taken, we'd moved all of our x's and then we would have moved all of our points up 3 units, the same as we've always done. So just by understanding a little bit of what the transformations do, then that will help you as you go through. What this does, this number changes your domain. It shifted it over. Anytime you deal with the x, that's going to change your domain. If we wanted to look at just a few problems where we dealt with just the domain and what our domain would be on these problems, if we had g of x is equal to the log base 3 of x plus 1. Now, if we want to get what our domain is, what we know here is that we would be undoing that, so we would be subtracting 1. And so our domain then would be from -1 to infinity. Another way of doing it is that value's got to be greater than or equal to 0, because we've said that this number, whatever it is, has to be greater than 0. So if that's greater than 0, then x has to be greater than or equal to -1. So our domain would be -1 to infinity. If we have g of x is equal to log base 4 of 2 minus x. Well, again, this number has to be greater than or equal to 0. So if we do that, then we have subtracting 2 and dividing by -1, we had to switch. So x has to be less than 2. So that means that our domain would be from -infinity to 2. And those are the values then that when you substitute in will give you a positive number here, a number greater than 0. If we have g of x is equal to log base 5 of x minus 6. Well, again, x minus 6, We know the undoing that we're going to would be a positive 6, so we're going to shift 6 units to the right. But we can also do it by saying this number has to be greater than 0. So x has to be greater than 6. So it would be 6 infinity would be our domain, would be the value that we would go. X equals 6 would be our vertical asymptote. So you can go through and deal with just the domain by looking at the functions. Okay, there's just a few more properties that we want to look at with our logarithms. And this is really where logarithms start getting to be a little bit of fun, not necessarily in the graphing part, but in the evaluating part. And so we want to look at some properties of logarithms. We're going to have what we call our general properties. This is for all logarithms. Then we're going to have what we call our common logs. And the common log is base 10 because that's our number system. And then we have what we call the natural logs. And that was the base e. I mentioned that a little bit earlier. It's when it's to the base e. And we also deal with that as this is the ln. Now, when we have base 10, a common log, we just write that log. If it's going to be any other base, then you have to actually put the base. But if you leave that base off, then we would just call it log. If it's the natural log, we would just call it ln. So one of our properties, and we've already looked at these in the general, we looked at the log base b of 1 was 0. Well, in our common log, the way we would write that is just log of 1 equals 0. That 10 is understood to be there. And when you look on your calculator and you see an log button, that is base 10. On your calculator, all you have is base 10 and base e. And then our natural log of 1 would be 0. Log base b of b, we found out was 1. And so again, the log of 10, since that is your base, is 1. And over here, the natural log of e would be 1, because e is your base here, 10 is your base. Log base b of b to the x is x. So the log of 10 raised to any power is going to be x. And the natural log of e raised to that power, any power, is equal to x. And then the other one, an inverse property, was b raised to the log base b of x. Remember, when the base of the your function was the same as the base of your log, then it equals x. So this would be 10 raised to the log of x would be x. Again, when no base is shown, it's understood to be a 10. And e raised to the natural log of x would be x. When it's a ln, then it's base e. So we can use this to evaluate without a calculator. If we wanted the log of 1,000. Well, 1,000 is 10 cubed. So this is the same as the log of 10 cubed, which would be 3. If we have the log of 10 to the 8, that's simply going to be 8. The base of my log is the same as the base of my number, so it equals the exponent. 10 raised to the log 53 is equal then to 53. The base of my log is the same as the base of my number. The natural log of e to the 6 would simply be 6. The natural log of e to the 9x would be 9x. The base of my log is the same as the base of my number, so it equals my exponent. E raised to the natural log of 5x squared The log, base of this log is the same as the base of my number, so it equals the 5x squared. And the natural log of 1 over e to the 7. Okay, that's the same as the natural log of e to the negative 7. So it equals negative 7. So by using those properties, you can go through and evaluate a good many things. And we're going to work in the next 2 lessons, we'll work a little bit more with evaluating logarithms and with using logarithms to solve problems. When you get to solving for your exponent, then you have to use logarithms. And it's one of the things that even a calculator isn't going to be able to get the answer without your understanding exponents.